what one has to appreciate is the intensity of energy. I always like to, I'm an engineer by background, so always like to tell people the mix of energy doesn't matter. How much is wind, how much is solar? We like to advertise that. Kilojoules matter because energy intensity has to shift, not the mix. So solar power cannot produce cement. Solar power cannot produce steel.
It cannot.
They are very energy intensive.
That's right.
Do you though? Like, are you sure? Because that claim sounds confident, but it's stuck in a how we've always done it mindset. Hey, I'm Robert, and for the last 2 years, my team and I have been developing an open source mining and refining technology. I'm here to tell you right now, the core tech behind what we're building, ion exchange membranes, has a way bigger application than most people realize. And yeah, I know that sounds like a big claim, but today I'm gonna keep it grounded. Steel. If you people want it, I'll do a separate video on cement. So the argument is basically you need gas heat to make steel. And I get why people think that, because traditional steel making does rely on heat and cold. But that doesn't mean it's the only way to do chemistry. Let's quickly recap on what the current process actually is. Steel starts as iron ore, which is basically iron oxide, aka rust. The classical process uses coal, carbon to rip out the oxygen out of that rust, and you end up producing CO2 and iron metal. But here's the catch. Because you're introducing carbon, you don't get clean iron. You get pig iron, which is iron loaded with carbon and it's brittle. So then the industry has to do another step. Blow oxygen back through it to burn off the carbon until you get the steel grade you want. And during all this, you get slag. And that slag contains a lot of iron. End result, you might only get 80 to 90% of iron from the original ore into the final product. The whole industry works because it runs on dirt cheap coal and high grade ore. And high grade ore matters more than people think. A lot of workable ore is quoted as needing 60% iron to be economical in traditional processes. But here's the chemistry reality check. Iron commonly shows as hematite, iron 2 oxide 3. So if you do the molar weight math, pure hematite is 70% iron by mass. So when someone says 60% iron ore, they're basically saying we need ore that's already close to pure rust. That's how dependent the old method is on high purity and cheap fuel. So the real question isn't, can solar produce steel by doing the same exact cold process? The real question is, do we have alternative processes that run on electricity instead of burning carbon? And we do. Because at the bottom of it, chemistry is electron movement. All reactions are basically electric interactions. We just usually force them through using heat because heat is a blunt tool. So here's an alternative approach: ion exchange, electrochemical extraction. Instead of heating rock to an insane temperature to force reactions, you dissolve the material and move the ions with electricity, and then plate off the metal. One big advantage, when you dissolve ore in acid, you can extract metals at extremely low concentrates. I'm talking parts per million, even parts per billion. And this is consistent with what we've already demonstrated with platinum group metal and rare earths. So instead of dealing with material and ore that's mostly rust, we can extract from lower grade feedstocks. One thing that people get confused is when they look at batch experiments for ion exchange electrolysis, you'll see recovery yields, number that vary, but the key is this. Batch electrolysis has a curve. As concentration drops, it gets harder to plate out the last bit. But in a continuous process, you don't hit that wall in the same way because you keep feeding dissolved ions into the system. That's why you'll see studies reporting near total recovery for some metals under the right conditions. But it's not magic. It's electrochemistry plus smart process design. But viewers are going to ask a real question. What is the cost? Let's do steel in terms of electricity. We'll use hydrochloric acid to dissolve the iron into ferric chloride. Now again, you might ask, what is the energy cost to make the hydrochloric acid? And here's the fun part. None. It's a continuous process. As we reduce down the dissolved ferric chloride to pure metal, we also regenerate the acid. So the only part that's important to calculate is what is the reduction potential of that ferric chloride. How much energy does it take to reduce it down, plate it off, which will automatically regenerate the chlorine. And here's the important part people miss. In electrolysis, reaction production scales with current, not voltage. The voltage just has to be high enough to drive the reaction. Past that, extra voltage is basically waste. Ion exchange membranes do add some resistance, so voltage might need to be a bit higher, but not dramatically. For this reaction, we'll run at 1.5 volts. See the screen for full conversions and equations, but the end result is about 1,960 kilowatt hours per ton of iron. At 8 cents per kilowatt hour with industrial prices, that's less than $160 per ton. Even if you add 10 to 20% losses, we're still well below $200. In fact, we can double the efficiencies and still be competitive. Because the traditional steel production process with blast furnaces has a cost of over $500 per ton. Again, please see reference material on screen. This is due to multiple stages required of heating, production of oxygen, coal, limestone, gas, and many other intensive energy requirements and ingredients to make crude steel. The iron ore itself only costs $100 a ton. Again, this is for pure high-grade iron ore. We can use much lower grade ore that's thrown away. And yet instead, we can produce high purity iron, which is actually really expensive to make traditionally. So this is some cheap steel. This is higher grade output category. You can still add carbon and make traditional steels as the manufacturing processes see fit. This additionally unlocks entire new industries to use pure iron economically. And furthermore, creates very, very high-grade steel, which I'm sure many welders and fabricators are going to love hearing this, knowing the frustrations with today's poor quality steel and iron from certain international sources, and those that have worked with historical steel knowing it's much better quality. So no, it's not against physics. It's literally physics. It's just not the 1900s blast furnace version of physics. If you want, I'll do a part 2 where I go deeper into cement and why ion exchange membranes are the key technology to some absolutely wild stuff.
You still need a gas-based heating or
and even
oil.
after 3 or 5 more years of innovation and renewable,
It's
not there?
physics. It's against physics.
Fine, absolutely.
So physics don't allow
right.
it to do it.
That's it, against
So
physics.
therefore, when you have to look at energy mix change in context of joules of energy, your challenge becomes different because the world still need to progress. World needs to build more infrastructure. It still needs steel. It still needs cement. It still need fuels.
So this sounds smart, but it's kind of a tell because yes, everything is energy, joules are real, nobody's denying joules. But this argument usually is used to smuggle in a bad assumption that industry chemicals must be done with heat. But when you talk about joules in this context, people usually think of thermal joules, heat energy, like how much gigajoules does the kiln need. But electrochemistry doesn't work by heating the entire system until atoms get bullied into reacting. It works by controlling electrons. In electrochemical terms, the lever you pull is the electric potential and current. Voltage determines whether a reaction is possible/favorable. Current controls how much reaction happens per unit time. So heat is brute force, electricity is targeted. Heat is like trying to write a sentence by writing the whole book on fire. Electrochemistry is like using a pen. And ion exchange membranes add another layer. They let you control which ions move and where, meaning you can drive reactions with much more precision. That is why this tech is such a big deal. Also, yes, membranes are effectively nanoscale technology in practice, which is why they can behave like entropy control hardware. The historical limitation has simply been cost. That's why our innovation is so huge, because lowering membrane costs is the key that unlocks and changes what's economically possible. As a comparison, commercial membranes cost in the hundreds of dollars for a few square inches, while our membranes are made from off-the-shelf components and cost less than $1 per square foot. So no, it's not against physics, it's literally applied electrochemistry. So I hope this video lets you see that the entire world is tackling these problems from the wrong perspective, justifyingly so due to the cost of the membranes. But this changes today. Stay subscribed for more revolutionary breakthroughs.